we're going to be going over for the rest of the PyTorch section of this talk. What we're doing here is that we have a set of parameters. N is basically going to be our batch size. Dn is the feature, the number of features that are going into a linear layer, and then the number of features going out of the linear layer. Again, I've picked powers of 2s just because I like powers of 2s, but it only has to be a multiple of 8. We're creating 2 tensors, and then we're wrapping them into a variable. For PyTorch, variables being the type that you have to be to basically record the graph operations. We are setting them to the batch size of 1 to the batch size times the number of features going into the linear layer. And then the second tensor we're going to be using as a target. So that one we're setting to the number of features that are coming out of this linear layer. We throw a .CUDA on these, and that's going to send it to the GPU. And then also we're going to just create a model. This model can be any model that you have. It doesn't have to just be a linear layer, but for the sake of being concise, we just have a single linear layer sitting here, going from the number of features in to the number of features out. And then that also we're going to put onto the GPU. We're going to send the parameters of this model over to an optimizer. So this is just the built-in PyTorch optimizer. And then just you have to give it the parameters of the model that you're looking to send to it. And then other parameters associated to SGD. So here we've just set a learning rate of 1e to the negative 3. Again, this is just for the sake of a concise example. Your scripts won't necessarily look quite like this, but hopefully this is a good representation of different parts of what your training scripts will look like. So then we're running through 500 iterations, and again, just an arbitrary number selected for the sake of this example. We're going to take the model, we're going to send into it our input tensor that we first created, actually wrapped in the variable, and that's going to give us an output. We're going to send this output to an MSE loss with our made-up target, and we're going to compute the error. It's going to give us the loss, and then we're going to zero out the gradients in the optimizer. We're going to call the backwards pass, and then we're going to step the optimizer to update the parameters based on the gradients that are computed. So we're going to go from start to finish with this example, showing you each incremental step that it takes to get this in a very safe position for mixed precision training that'll allow you to maintain the accuracy that you've been having just as it's written here or as your script will be written in FP32. The first trick, of course, is that we want to change from single precision to half precision. For PyTorch, the default precision for CUDA is single precision. So the first thing we have to do is we have to put .halves on both the variables, because we want the data in the variables to be in half precision, but also for the model, because the model contains the parameters, and we want the parameters in the model to be FP16 as well, because they're going to go, the parameters in the models are the ones that are going to get eventually sent to the kernels, and we want all the values sent to the kernels to be FP16, especially for this linear layer here. And in theory, that might be all you have to do. It is very network dependent. For image networks specifically that have something like batch norm tends to help a lot in FP16. You might actually be able to get the same accuracy you saw before by just doing this. But sometimes you do need mixed precision. So this is the pure FP16 case that I was talking about. This is everything is done in FP16, nothing being done in mixed precision. The first thing, though, that we're concerned about is that the weight updates are actually going to be fairly imprecise the way that we are doing them right now. And what I mean by that is, what is 1 plus 0.0001? Well, you're obviously going to tell me, well, it's 1.0001. Yes, FP32 will give you that result. FP32 has the precision to update that small value with the not so much larger value. Half precision does not. If you send this to half precision, you're going to get 1 back. You will completely miss that extra little bit that you were trying to update. And so I've given the actual threshold right where you will see if your original value is updated. But we want to avoid this because gradients in when training neural networks can be pretty small compared to the parameter. And if you're doing a lot of updates that are much smaller than your parameter, you're going to miss all of those updates. They're not going to show up. You're not going to get the value of those gradients being added to your parameters. So this shows up in our example right when we send this model.parameters to the optimizer. Remember that the parameters in the model are FP16, and that is what we're using to update based on the gradients that we calculated when we trained our network. So I'm going to introduce to you the mixed precision life cycle, we like to call it. So we start with converting our network to FP16, which means that all the parameters, all the weights are now in FP16. We run the forward pass, and then again we have an FP16 valued loss. We do the back propagation, and then we're going to get FP16 gradients. So this is kind of where the trick starts. I mean, we can represent small values in FP16. We can represent that 0.0001. The problem comes in when we try to do a mathematical operation by adding it to the value of 1. Since we don't have a large range that we can work with in FP16, it means once we add it, it's not the addition cannot be, or the total value cannot be represented in FP16. That 0.001 is too small compared to the 1. But it is representable in FP16. So we do have 0.001, 0001, represented in FP16. We have 1 represented in FP16. We want to add those two values together. We want to add them in FP32. So what we're going to do is we have this FP32 master copy of the weights that we're actually going to create before we do anything. They're going to be synced up with the model. So the model is going to have FP16 weights. We're going to have an extra copy in FP32. And every time that we do an update, we're going to first take these FP16 gradients, convert them to FP32, and then update this FP32 master copy of the parameters. And now we have maintained all the value of that update. We are taking those gradients that are representable in FP16 and applying them in a way to the weights that is also representable, so we can get the benefit of that gradient. And then before we go into our next forward pass, we're going to make sure that this master copy in FP32 is synced up with the model. That way, the next time you run the model, you're going to have the updated weights. So for this, we have a little helper function. What our helper function does is it's going to take your model. You're just going to send your model to this function. It's going to grab all of the parameters from that model and create a new copy that's in FP32. So what it's going to return is it's going to return a list of your model parameters. That's the original FP16 model parameters. And it's also going to return a new master copy of the parameters, which are in FP32. This way, you can just throw it to the function. You can get your extra copy of this FP32 parameters, and it should be easier to kind of keep track of all the things that are going on. And in fact, integrating this into the example, we run through this utility function. We call it prep the parameter list. We send the model to it, and like I said, we get the two sets of parameters back. So now that we have this FP32 set of parameters, we can send those to the optimizer. Now, when the optimizer actually steps, it is updating the 32 weights instead of updating the FP16 weights directly. One trick that we have to keep in mind with this is that before you do the backwards pass, we don't care about zeroing out the gradients in the FP32, because when the backward pass runs, we're actually going to be computing the FP16 gradients. So we need to remember to zero out the gradients on the model itself that has the FP16 gradients, which are going to be updated before we run the next backwards pass. This isn't complete, because now we have this master parameter that are the FP32 copies, and yet we're running the model that are the FP16 parameters, and we've never actually synced the two parameters together. So that's what we're going to do next. Again, a nice utility function. We're trying to keep these utility functions fairly concise to make converting your networks easier. So this one is going to take the master parameters. It's going to take the model parameters that we created. And what it's going to do is it's going to copy the updated master parameters back into the FP16 parameters. And the way to use this is that after the optimizer step, after we have just updated the after we've updated the FP32 master copy, we're going to copy those parameters back into the model so that the next iteration, when we go through the forward, it's going to be using these updated parameters. We also have to do the inverse. So we actually have the gradients computed in FP16, but those gradients are supposed to be used to update the FP32 master parameters. So this is actually going in the opposite direction, but on the gradients. So this utility function will once again take your two lists of your parameters, the FP32 copy, the FP16 that's in the model, and then it'll take the gradients from FP16 and copy them into the FP32 gradients so that when you call the optimizer, now the optimizer will be run with the gradients that you computed from your backwards pass on the model. It'll be updated to the FP32 master copy of the parameters. So now we're going in both directions. And I'd like to run through this one more time because I know it's quite a bit to digest at once. But again, we have our model. We are computing our output. This whole thing is in FP16. We run a loss function on that, which is also FP16. It gives us an FP16 loss. We zero out the gradients for the FP16 copy that's in the model because those are the ones that are going to get calculated in the backwards pass. If we don't do this in PyTorch, it will actually add the new gradients to the gradients that you computed in the last iteration, which is not what we want to do. We want just the gradients from this iteration. We're going to take the gradients in the model, and we're going to copy them into the gradients of the master copy because the master copy is the one that the optimizer has. So now this optimizer step is in FP32. We don't lose any precision from trying to update our master parameters with small gradients because now those gradients are in FP32 and they're being updated to an FP32 master weight of the parameters. And now that we have a master copy of the parameters, we want to copy it back into the model. We want the next iteration that we're running, the model has those updated parameters to run on. So this runs you through our whole life cycle now, from having the FP16 weights, running the forward pass, running the backwards pass, copying those FP16 gradients into the FP32 master gradients, applying those gradients to the master weights, and then going back and updating the FP16 version so that we're ready for our next forward pass. So that's the first challenge. This trick by itself will get you a very long way to getting back to the convergence you were seeing in FP32 if you noticed that when you switched to FP16, pure FP16, that you lost the ability to do some of the converging. It is not necessarily the whole story. Some networks do take a little bit more, and actually FairSeek is one of those networks. So in FairSeek, we have an issue with the gradients underflowing, and that's the next battle that we're going to solve. The new place that we're concerned about is this loss stop backwards. So this loss stop backwards is going to propagate your gradients from the loss function all the way into every single parameter in your network. This is all going to be done in FP16, and sometimes the problem with this is that the gradients of a network can actually be very small. So the gradients that are getting computed are very close to zero. And again, FP16 doesn't have the resolution FP32 does close to zero. This big bar over here is actually the activations of a ReLU function. So if you have ReLU, a lot of values come out as zero. Those gradients are going to be zero. So we can ignore that for now. Now, what we would like to do is we would like to take all the values that are not representable in FP16, and we would like to shift them over to the right. So in order to do that, we have this trick called loss scaling. And all you basically do is you take your loss, you multiply it by some sort of scale factor. Whatever this scale factor is, will be shifting over to the right. So if we pick a multiple of 2, it's going to shift it over to the right one step. If we have a multiple of 4, it's going to go over to 2 steps because this is the log 2 magnitude of our values. So for example, we picked a factor of 128. That means that all of our gradients are actually going to get shift over quite a few bits. By shifting that exponent, we are pushing our gradients into values that are representable into FP16 out of regions where it may have just been truncated straight to 0. So the way that we do this is we multiply the loss value that we calculated by a scale factor. This scale factor is going to be part of the computational graph. So if we have 128 on the scale factor, that means every gradient that we compute is now going to be 128, a multiple of 128 larger than they would have been if we had a scale factor of 1. So now our gradients are 128 times larger, which is really no problem. So what we do is we copy those gradients into the master gradients. Now they're FP32 gradients. Now we have that resolution near 0, so just divide back out that scale factor. So we temporarily push the gradients into a larger value so it can be represented in FP16. When we convert them back to FP32, because we have to anyways to apply them to the master weights, we just divide it back out by the scale factor. Now your gradient is basically the same value it would have been if you did all of this in FP32. They are representable. We convert them to 32. We apply it to the master copy. And now all those values in the gradient that would have been 0 are representable and are applied to the master parameters. So what we've done is we've taken our life cycle that we talked about before, and we made it a little bit more complicated, but we just inserted really 2 more steps in this. One more time, we have the FP16 weights in the network. We compute our loss. We convert our loss to FP32, basically just because we're going to multiply it by a large scaling value. So we don't want it in FP16 because if we multiply 128 by an FP16 value, if that FP16 value was too large, it's just going to push us into infinity because FP16 won't represent it anymore. So just convert that loss value to FP32. It's just a single value. We're going to scale by that 128. We're going to get the scaled gradients of FP16, and we're going to copy them in FP32. At this point, they're 128 times larger, so we're going to divide those back out, or we're going to divide that 128 out. At this point is a good time if you have to do something like clipping. Clipping is definitely better done, depending on your clipping method, in FP32, so this is a great time to do your clipping. You'll have your FP32 gradients, you'll apply it to the FP32 master weights, and then you'll put that back into your FP16 model, and you're ready for the next iteration. So now we have tackled the second big challenge at FP16. The last one that I mentioned was that your reductions may overflow, and so actually in our value we do have a large reduction, and that is this MSE loss function that we're using to compute our error on this example. So the problem with reductions I mentioned before, and now just illustrating it in code, is that if we have too many relatively large values, it is a lot easier to overflow FP16 than it is to FP32. So if we have 4,094 values of 4, and we try to compute a norm on it, well, what happens is as we're computing this norm, at one point in the calculation of the norm, we actually overflow in FP16. And even though the result would be representable in FP16, since the computation of the norm overflowed at one point, that means that we can't recover from it. So FP16 is actually going to give you a NaN if you just push this 4094 to one more value. So all it took was that one extra value from getting a nice good output of 256 to something that should have been very close to 256, but in fact, since the computation hit inf, it can't recover from that. We no longer know what the value is supposed to be. So this is actually a pretty easy fix. We were about to convert the loss to FP32 anyways, so really what we do is we just convert the tensors that we're going to send to the loss to FP32. Now that those tensors are FP32, this operation will all be done in FP32, and then our loss will no longer overflow. So if you do the conversion to FP16, and you're running through your iterations, and all of a sudden an inf or a NaN shows up in your training, you're not really sure why, this is one of the bigger reasons this tends to happen. You probably have a large reduction somewhere in your network, and that reduction happened to overflow, and you can't recover from that. Another reduction that we encounter often is batch norm. This is still an open question of if we need batch norm in FP32. It does appear that pure FP16 batch norm does work for a lot of networks, but some networks we might want to just really err on the very careful side. And so what this is another utility function, because I love utility functions. It takes your module, and then or your model, the entire model you send to this, and it will search all the way through it recursively, and it will convert the batch norm layers into being FP32. And once those batch norm layers are FP32, it's going to do the actual parameters of the batch norm in FP32 instead of FP16, and it tends to be a little bit safer in case you're a little bit concerned. So this is our total mixed precision solution that we're going to present to you here. We've taken care of the weight updates, the gradient underflows, and the reduction overflows. The other thing you should take into consideration, just a practical matter, is when you're creating checkpointing, you want to checkpoint and save the master copy of the parameters. If you only save your model, you'll only get the FP16, but you went to all the trouble of computing the FP32 master parameters, you should save them. You should reload them in. And then also you can save the gradient scale factor, so that loss scale factor that we were talking about.